All right, I'm back. So we were going to look at a horizontal projectile, but in the opposite way. So I'm going to launch something off of a cliff into some water. So here's my cliff. Here is my water. I'm going to start the object up here at the top of the cliff. I'm going to launch it off horizontally. So I have some initial velocity in the x direction, but not in the y. It will go down, make this little parabola shape again, but then it will hit the water down here with some final velocity, but that final velocity is at an angle to the water. So I'm going to tell you what the displacement in the y direction is, and I'm going to say that that's negative 100 meters. And I'm going to tell you what the displacement in the x direction is, and I'm going to say that that's 30 meters. And we're going to use that information to find that final velocity. So what is our final velocity? So since my delta y is 100, that makes this distance right here, my y distance 100. Sorry, those arrows were a little shaky. Okay. And then my x is going to show you that 30 is this distance right here. Okay. So first thing I'm going to start with is trying to find how long it takes this object to reach the water. So knowing that time is going to be vital in being able to solve for the final velocity. So I'm going to start with the equation delta y is equal to v naught y t minus 1/2 gt squared. But it's a horizontal projectile, meaning I have no initial velocity in the y. So that makes this negative 100 is equal to negative 1/2 g. I'm using 10 for g, so that makes that negative 5 t squared. So if I type that into a calculator, which I've already done, I'm just to save some time, I'm going to say that's 4.47 seconds. Okay. So then I'm going to use that time then to find what my velocity is in the x direction, because that's the only velocity given in the picture. Now it doesn't give me a number, but this would be the velocity that I'm launched off of the cliff with, our v naught x. So delta x was 30. That would be equal to our initial velocity in the x times our time, which is 4.47. So the time in the x direction and the time in the y are the same because that object is doing the motion all within the same time period. So our initial velocity in the x, which would also be our final velocity in the x because there's no acceleration, is going to come out to be 6.7 meters per second. All right. So then next thing I want to find is my final velocity in the y direction. So I have it in the x direction. I want it in the y direction because I'm going to find my total final velocity. So to do that, I'm going to do v final y is equal to the initial y minus our acceleration times time. The initial velocity in the y is 0. So v final y should be equal to negative g, which is 10, times our time, which was 4.47. So our v final in the y direction would be negative 44.7 meters per second. So notice that my final velocity in the x is a positive value because I'm saying that to the right is positive. And then our final velocity in the y direction is negative because we're saying down is negative. So it's moving to the right and down at the same time when it hits the water, which matches our scenario of an object that is moving down into the right. So I'm going to combine those together to find my final velocity. Neither one of those are the final answer because this object is moving down. Oh, I don't want that to be highlighter. Try again. This object is moving down and it's moving over when it hits the water. So the final velocity is going to be at an angle like this, the total final velocity. So our hypotenuse would represent our final velocity. This side would be the final velocity in the y. This side would be the final velocity in the x. And I have both sides of those triangles. So when I have both sides of the triangles and I want to find the hypotenuse, I could do some a squared. Oh, I don't know why I did equal, sorry. A squared plus b squared is equal to c squared, where c is our hypotenuse. So c, or our final velocity total, would be equal to the square root of vx squared plus vy squared. So our final velocity is going to be equal to the square root of our 6.7 squared plus our 44, or negative 44, I guess, 0.7 squared, okay? But when I square root a negative, it becomes positive, right? So our V final here is going to have a magnitude of 45.2. So 45.2 meters per second. Now, that is just the magnitude. So before, our direction was just a positive or a negative. But now I'm moving in the positive x direction, but the negative y direction. So that's not going to work anymore. So now I have to describe my direction as the angle that that object hits the water with, or hits the ground with, or whatever the scenario is. Okay, so you can use any type of trig that you want because you know all the sides of that triangle. Okay, I'm going to use the tangent function here. So tan theta is equal to opposite over adjacent. Okay, so that makes theta equal to inverse tan of opposite over adjacent. And if I'm looking at our triangle above, then my opposite value is my velocity in the y direction, and my adjacent is the velocity in the x direction, the final x. All right, so our theta would be equal to inverse tan, and I'm just going to use the magnitude. So you don't want to use the negative here. You want to use the magnitude of these values. So V final y was 44.7 over V final x, which was 6.7. So our theta comes out to be 81 degrees, which is pretty big. But I just made up these numbers at random. So there's that. So when I'm describing my velocity, I want to say it's 45.2 meters per second at 81 degrees. So that's my full answer of magnitude and direction for the final velocity as our object hits the water. All right, so use this information to solve example set 1, and let me know if you have any questions. Bye.